All right. Good afternoon, everyone. Today's colloquium is by a familiar face. Larisza has been here in Boulder since 2011 and has been a long-term visitor at HAO for quite a while, obviously. So today she's going to talk to us about Dimmings in coronal holes. And Larisza, not in coronal holes, okay, Dimmings. Larisza got her master's degree at Eötvös-Loránd University in Hungary, Budapest. She then did her PhD at Trinity College in Dublin, Ireland. And after her PhD, she moved here to Boulder and moved to a position at CU Osiris and has been there ever since. So, Larisza, go ahead.
Thank you. Hi, everyone. Thank you for coming. So today I will talk about dimmings, but not just any dimmings, foot point dimmings. So I'm introducing a new name for these dimmings. So just a quick overview. I will first introduce dimmings just in case we have anyone here who needs a little brush up on what dimmings are and how we used to observe them and how we can observe them in a different way. And then I will talk about the algorithm that I developed to identify dimmings, statistical results, and connection with eruptive events. And finally, the morphology to sort of ideas and thoughts about why dimmings look the way they look and why they are so odd. So what are dimmings? Many people actually call dimmings transient coronal holes. I think that term is starting to catch on because originally people called them dimmings because something went dark. But over time we realized that actually they are pretty similar to coronal holes. The main difference is how this open magnetic field region is created, because both coronal holes and dimmings are regions in the solar corona where you have open magnetic field. Coronal holes tend to live a long time, sometimes several months, over a year. Dimmings, a few hours, over a day, something like that. Not really long. So, hence the term transient coronal holes. So these dimmings or transient coronal holes are created through an eruption, where essentially if you have a coronal mass ejection, the magnetic field opens up temporarily, and this temporary open field is the dimming when you look at EUV images. So the dimmings are essentially the foot points of the CME structure, and if the stars are aligned in the right way, you might even see 2 foot points. And so this is the classical idea of a dimming structure where you have the 2 foot points of the CME loop. One is mainly positive polarity and the other one is negative polarity. The reality is that dimmings don't look like that. In fact, it's very rare to have a perfect double dimming. So the way to observe them is to look at dark regions in EUV images. Look at movies. That's the best way to spot them. And why are they dark? Because there's mass depletion due to the expansion or mass outflow. Oops, that was a movie. I should probably show you. Here's a dimming. Boom. So there's a nice big eruption very close to the center of the sun. Beautiful, straight down the hole. And you can see how it appears and it disappears. So the magnetic field opens up, there's an eruption, then the field starts closing down, and it fills up with plasma, becomes bright again, dimming disappears, gone. So I'm going to just quickly play this for you. You want to look at the center of the sun. A few hours. Less than a day. I can't see the numbers. But I think it's less than 12 hours. Okay. But I will also show you statistics on the lifetimes of dimmings later on. So, let's talk about the types of dimmings. So when people hear about dimmings, we have the classical idea of a double dimming, 2 foot points, and here is an example. Mind you, not the best example, it's a rather faint one. So here is the movie, and you want to look around here. This is the area. I'm going to play the movie again. Here, you can see 2 faint dimmings appearing there. Now, if we zoom into that region, and this is what I do, ignore this image, you don't have to worry about it just yet. This is what we want to look at. So once we contour the dark regions there, at the peak of the dimming, you see two regions, the 2 foot points. At least we like to think that those are the 2 foot points of the erupting loop structure. So if we dumb it down into 2D, here's your loop structure, it's erupting, and it's these 2 foot points that you can see. And if you look at the magnetic field in these two regions, you will find that one is dominated by a positive polarity and the other one by negative polarity. So that's a good indication that that might be the case. Now, a lot of the time, we see single dimmings. The way I define, so these definitions have been introduced by moi. You can find it in the paper that has been published earlier this year. So we started with the double dimming. Now we're introducing single dimmings. The definition is that you have one large dimming. You might have little fragments around it. They might be evolving, changing in time, but the requirement is that you have one big dimming. So this is the first example I showed near the disk center, one large region evolving over time. And then you have fragmented dimmings, where there is no one big dominant dimming, but lots of little fragments. Here is a movie of that, and you want to look around here. So once you zoom in, this is what you see, lots of little fragments evolving in time. And then, of course, there's a zoo of weird cases, which were not included in this study. So in the catalog of dimmings that I've created, we include double, single, and fragmented dimmings, but we don't include cases like filament eruption dimmings, where there's so much obscuration that we cannot precisely determine how the area has evolved or how long the dimming lived, because the obscuration means that it might be still there, we just cannot see it. So here is an example. Up here you want to look, you can see a dark region appearing, but because of the rising bright arcade is obscuring the dimming, we will not include this in the statistics. Another one, which is very curious and interesting on its own, I think it deserves a whole research on its own, is dimmings that join existing long-lived open field regions, coronal holes, and so the eruption happens near a coronal hole, and this dimming pops out and sort of just like joins onto the coronal hole. And basically, the coronal hole becomes larger, and that dimming does not quite disappear or just changes in time. It's hard to know what happens there. Here is an example. Here's our coronal hole. There was an eruption. It's sort of joined around here. Play it again. This is where we're looking. It's hard to know what happens there. So historically, how do we identify dimming? Because dimmings, as you've seen in the movies, a lot of the time are pretty faint unless they are massively large and bang in the middle of the center of the disk, it's hard to visually notice them. So a lot of people very cleverly decided that difference imaging is the way to go. And in fact, difference images are an excellent way to identify the location of dimmings. So what you do is you can do two different ways of identification of dimmings, is base difference and running difference. Both are great. Base difference, for some of you, if you need a little reminder, base difference is you take a picture before the eruption of the sun, and then you subtract that image from each frame later in the time, and that's how you build a movie of the changing image. So here's an example by Gemma et al. This is the beginning of the dimming appearing in this region, and as it changes over time, it is the dark region that is meant to be the dimming. And Alicia Reinhardt, my co-author, had also identified dimmings using difference images. Another method is to do running difference images or movies, and here you subtract the frame before the frame that you're looking at. So you're always subtracting the one before. And so this is great for looking at how the intensity evolves over time. And here you see even small changes of intensity. And that's why dimmings in these identification methods look massive, absolutely huge, diffuse. The boundaries are pretty fuzzy. It's hard to say where the dimming ends and where the quiet sun begins. For example, here's an example. This is before the eruption. Then as the eruption carries on, you can see that there are lots of little parts of it, and it's hard to say, like, where does it end, where does it begin, and what do you still include if you try to study the evolution of the dimming. On disk center, same story. Dimmings are pretty large, and as you follow them over time, they kind of fall apart and fragment and often even cover up the whole sun. And the reason for this, and I'm sure many people will agree, is that we're not just looking at the foot point of the erupting loop structure, but the loop structure itself. So as the plasma inside the CME is rising, that very faint change in intensity as this plasma is rising above the disk, we can spot that with difference images. So I think this is an important thing, because we talk about dimmings. A lot of people have measured the physical properties of dimmings and made associations with CMEs. And if you don't remember anything at all from this talk, this is the take-home message. When you compare a difference image dimming with a CME, you're practically comparing two of the same things. You're comparing the CME with the CME. So of course you will have beautiful correlations. You will say that yes, giant dimmings correlate with big CMEs. And I'm sure that there is some relationship, but it's important to note that we're not just looking at foot points here. So the harder way to go around this problem is to look at dimmings directly. So this is quite a tricky thing to do, because often they are faint. Here is an example of a direct detection of the famous double dimming of 1997. What it looks like if you directly look at the dark region, essentially the temporary coronal hole, and what it looks like in a difference image. So you can see the boundaries are pretty sharp in the EUV image and pretty fuzzy in the difference image. So there is, and of course, if you track this over time, then they look completely differently. The primary difference between a foot point dimming, and now I call these difference image dimmings projection dimmings, is that foot point dimmings, what they do is that they start off from a little seed of a dimming, they grow over time, and then they contract and disappear, possibly to the same location or very close to the location where they originated. Projection dimmings, they appear and get bigger and bigger and really massive, and then they just kind of blend into the background. So they don't contract back into the region where they came from, because the plasma has expanded so much, and that's what we're looking at. So I think it's very, very important that we make a difference between what we're looking at. Okay. So let's carry on and talk about the direct detection of dimmings. So the algorithm that I developed is called CODIT, or Coronal Dimming Tracking Algorithm. And it uses EUV images. Primarily, I use SDO-AIA 193 images. And basically, I use low intensity region detection by a local intensity histogram thresholding. Just a quick run through. I start with the full disk image that's transformed into a Lampert equal area projection map. This is done to make the detection easier. I use different size windows to go through the image to identify the low intensity regions. Because the hole detection method comes from coronal hole detection, this is how it was done. And once the low intensity region is identified, then the contour is applied, and hence you have your dark region. Then you look at magnetograms in the same region and you see if there is a unipolarity. If the region is unipolar, you're probably dealing with a coronal hole or a transient coronal hole. But the difference for the dimming detection is that we don't use the whole of the sun, the user comes in and says, okay, I know when the dimming appeared, it was in this region. So the method is semi-automated at this point. All the user has to do is click on the image to define a box where the dimming has appeared at the time when the dimming was observed. From that point on, the method is completely automated. The algorithm will basically identify the dark region in that frame, and using 7 images. Blah, blah, blah. I think I explained that already. And then once the region is identified, let's say here's a dimming that we want to track in time, this pink little one. So what the code does is it tracks it back in time to find where it came from, what the seed was. Once we find the location and the start time, then the code runs again from that point on and tracks that region until it disappears. So then from the seed region, the dimming grows, sometimes even splits into smaller parts or moves around, and then it contracts. So then we have the whole evolution of the dimming region. And an added bonus is that we can even, based on knowing where the pixels of the dimming region was, we can track splitting parts. So we can study the dimming as a system rather than just a single region. Once we identify the dimming, we also look at the magnetic field properties. So we overlay the contour onto HMI magnetograms just to see how unipolar it is, how the magnetic field changes in the dimming region. And the properties that we can identify overall is area, lifetime, the intensity threshold, mean EUV intensity, photospheric magnetic field, and where the location of the region is. So the dimmings are chosen, after the dimmings are chosen, they are tracked over several hours or as long as it takes to follow them. And so here is an example output of the algorithm. This is the original Lambert equal area projection map with the region of interest shown in the green box, and the dimming is the pink region inside. Here it is zoomed in, and then the HMI magnetogram sub-image for the same region. Here's the dimming of interest, and then the histogram showing the magnetic field distribution outside the dimming, that's the black line, and inside the dimming, which is the pink line. So over time, you can even create a movie of this histogram changing, and you can follow the pink histogram basically becoming more unipolar. You can see how this dimming changes in its magnetic field. So all in all, the statistical study that I did was for 2013. In this 1 year, 154 foot point dimmings were identified. The identification was done manually. So I looked at daily movies for every single day and created a catalog of each dimming. And then after that, I ran the algorithm by clicking and pointing at the right frame. And then the algorithm did the analysis for that specific dimming. So that was done for 154 dimmings. And then these dimmings were also visually linked to flares and CMEs using the GOES X-ray catalogs and the Cactus, I think it was Cactus, a CME catalog. And so the dimmings were, where possible, the dimmings were paired with their eruptive counterparts. So this work was published earlier this year in AbJ, so you can look it up if you like. So here are the results. The most interesting finding, which is not terribly surprising, is that large dimmings, I don't know why I wrote kernel holes, it must be like just the back of my mind just writes kernel holes for everything. Large dimmings tend to live longer, but it's also true for kernel holes. So basically, the idea behind this is that if you open up a closed magnetic field and you've opened a lot of it, then of course it's going to take you longer to close that field down. The next finding, so these are the two diagrams I want you to look at, the one that I circled. So the first one was the correlation between the area of the dimming and its lifetime. And so the correlation coefficient was very nice and big, 0.7, so I even believe it. The other one was that smaller dimmings acquire a higher magnetic flux imbalance over time. So translated into what makes sense is that smaller dimmings tend to be more unipolar than larger ones. So for some reason, these loop foot points are more concentrated in smaller dimmings. I don't know why. It would be very interesting to find out. And so this is the diagram that shows that relationship. The correlation coefficient is 0.4. So it's a weak correlation. I would just admit it and just point it out. The next study was to look at basically an image before the eruption and then at the peak area of the dimming. So here's an example. Here's the dimming region before the eruption, and then it's at peak. So the pre-eruption image was 1 hour before the maximum area. Apparently, I forgot already. But so what we found was that the area of the dimming is not necessarily indicative of the mass removed. So basically, just because a dimming is huge does not mean that the CME mass is going to be huge. So big dimming does not mean big CME. What we actually found is that it's the intensity change inside the dimming that correlates with the mass and other properties of the CME and flares. So when we compare the intensity change overall, the intensity change correlated with the CME mass, angular width, and the flare intensity. Also, if we looked at the intensity of the region at that one given moment, the brighter the region was, again, the more correlation we found with CME mass and angular width. So it's all in the intensity. And if you think about it, it makes sense because intensity is related to electron density. Also, another interesting thing is that inside dimmings there are darker cores. And their behavior is even more important than the dark region itself. So when we looked at the lowest 10% intensity images, or intensity pixels inside the dimming, the correlation was even better. And in fact, the intensity change in those cores over time correlated with everything. The CME mass, the CME kinetic energy, the flare intensity, and the CME angular width. Again, nobody likes to look at tables, but I want to point out that the correlation coefficients are indicative of a weak correlation. Now, why is there a weak correlation? Is this a real physical reason for this? Or is it because the CME properties that we used from the catalog were estimated assuming that the CME was perpendicular to the line of sight? So I just want to point out that the errors in the CME properties that are available in this catalog are probably big. So the best way to fix this is to do my own CME mass calculations. Of course, it's going to take a long time, but basically by looking at quadrature, using stereo and SDO, and knowing that the dimmings that we look at in the center of mass were observed by another satellite, so to know that they are at right angles. But anyway, there is an indication of some sort of correlation. Let's move on. So morphology, that is the last point I will talk about today. But to me, it's a very interesting topic. So why do dimmings look so different? So I have a few thoughts on why. I combine morphology with the magnetic flux imbalance identified from HMI magnetograms. So there are three types, as I said previously, the single, double, and fragmented. So what are single dimmings? There are three different scenarios. I don't know if you can read this or not, but I'll just explain. So a single dimming can either be unipolar, dominated by a single polarity, or it could be mixed polarity. So if it does have a unipolarity, then perhaps what happens is that the other foot point is either obscured by a bright arcade or whatever feature, or the other foot point is spread out, not concentrated in a region to make it dark enough. So this is the case when we are dealing with a unipolar region. Another possibility is there is no flux imbalance, that the mean magnetic field is pretty much zero Gauss. In that case, it is a possibility that you're looking at both foot points in the same region. The foot points are so close to each other that it just appears as one enormous dimming. The double dimming, you know that already, 2 foot points. Typically it would be one is one polarity, the other one is the opposite polarity. The fragmented dimming, I would say, is probably a combination of all sorts of scenarios. Possibly obscuration, double dimmings mixed in there. It's just a mess of foot points. So what am I going to do next? Here are the plans. So I'm really interested in studying the cores of dimming regions because they seem to be more related to the eruptive counterparts. So basically I want to track these foot points and possibly their movements in time and look for signs of possible interchange reconnection or alternative processes. I would also like to separate the different types of dimmings and look at the statistics, because right now the statistics of dimmings is including everything under one roof. But it might be interesting to look at how, let's say, only single dimmings relate to CMEs and flares, or double dimmings. Is there a better correlation? And of course, the next step would be to fully automate the algorithm, so that no user has to do anything. It is basically on a daily basis, it would look at an EUV movie, identify all the locations of possible dimmings, and then analyze them, and then store them, and possibly correlate them with CMEs if there are any. And of course, it would be great to also bring in the KP indices, the geomagnetic disturbances. And the big question is, I suppose a lot of people are interested in dimmings, is because we want to use them to forecast geomagnetic disturbances. So the question is, can we just look at a dimming and predict how big the geomagnetic storm is going to be? So if we could do that, that would be amazing, because it would give us a few hours to prepare. But as of yet, I don't think that's working. But I don't know, we might be able to do that one day. So that's the end of my talk. Thank you for your attention. Questions? Anybody still awake?
Paul.
So I have a couple of different things. First, you say that you don't find a correlation with the CME mass and the area. It's more intuitive to me that I would think a stronger correlation with the integral of the change in density over the area.
I think combining the two might be a good idea.
And this is all only for one thing to me, right?
Yes.
So have you done anything where you look at different wavelengths and how different wavelengths in AIA that give you a kind of temperature distribution, and you can try and then do a PM or something to actually get a mass out of that?
I have not.
And then the second thing was about the correlation with the magnetic polarity. Or did you do any comparison balancing with the U angle? Like, do you see, is a map where it is on the disk, how much of a polarity imbalance you see?
I have not looked at that. I think that's a good idea. Typically, I try to stay within 60 degrees of the disk center so that I have less error in the magnetic field. But yes, that's a great idea. But I actually didn't look at correlation between magnetic properties and... What were you suggesting? I should probably look at that. No, it just, I basically look at the values, but I don't think I've done any correlation between magnetic properties. No, I pretty much looked at intensity in area and lifetime.
You were talking about filaments earlier with dimmings associated to them. Were they filaments that at some point evolved into a CME, or did they remain as filaments?
So if I see a dimming related to the filament eruption, I just throw it away immediately. Because of the obscuration, I don't even look to try to find if there was a CME related. In the example that I shown, my guess would be that probably there was a CME, but I don't actually know. Because those are excluded from the study completely.
Because the filament itself obscures the...
Well, it's not the filament, it is the rising bright arcade in the wake of the eruption. In fact, I think if there's a bright arcade afterwards, I mean, that's indicative that there was an eruption, right? There cannot be an eruption with no, or an arcade without the eruption.
So I guess my question was, do you think that coronal dimmings or transient CMEs are associated with filaments that exist that do not turn into CMEs? Or do you just not that?
So to have a dimming, you have to have open field length, and that means that the material is gone. So if it's a filament that, do we call them like a failing eruption, where a filament, I'm not even sure if that's possible, where a filament would erupt and then return. Maybe it's possible, but in that case, we would not see a dimming at all, because you don't have a temporary open field.
Great, thanks.
Yes.
Ricky?
What's the timing relationship between a coronal dimming and a CME?
I would have to look at the paper, but it's a few hours. It had to be within a few hours, and from the statistics, CMEs always, I know some people will beat me up for this, but CMEs occurred after the dimming. There are people who claim that the CME can happen before the dimming appears, but I have not seen that. So within a few hours.
Do you keep track?
And same with the flares.
You keep track of how much time there is between each event?
I have that data, yes. So if you're interested, I can give it off.
So what are you, in that sense, are you defining a CME by visible in Alaska or C2?
Yes.
And there is obviously a time delay between when it's visible there and when it's launched.
But I do not do the identification. So I use the... Which catalog is it? My brain is failing me now.
Cactus is one.
No, I don't think it's no, it's not Cactus. It's the Someone and Someone catalog. Yes, that catalog. And so I don't identify the chronology. I basically have my dimming list, and then I go and look at the catalog. And I would look at the movies just to make, so I look at the difference movies of the CMEs to make sure that the location is appropriate for where the dimming was and the CME, so that I make a correct match. But then any of the calculations that were done are not done by me. I just take the CME properties from the catalog and relate them to the dimmings. So I know for a fact, I think everybody knows that there are big errors because of the assumption that the CME is moving in the plane of sky, which is not the case. So in fact, let me plug in an advert in there. So I'm doing a new study where I only look at, so I'm looking at SDO and stereo quadrature time. So there's, I think, 3 years where they were at close to right angles. And so I'm looking at, what am I looking at? So I'm looking at, with SDO, I'm looking at dimmings that are near the central meridian, and then I'm using stereo A and B to find the CMEs. because then if my dimming is at the central meridian, then of course the CMEs would be at right angles with the stereo. So then I actually used the Angelus's code where I'd click and point where the CME is and try to do the estimate of the mass myself. So that will be, this is a follow-up study to see if the correlation improves. If it does not, then that's an indication that it's not the error in the calculations that is hurting the correlation between dimmings and CMEs. Does that make sense? Yes.
Can the dimmings be seen in integral emission?
I don't know.
What emission? Integral. The way that it is. I mean, that's.
Oh, as in like Eve? As, for example, like in Eve, EV.
Yes.
Isn't it? Yes. So James Mason, who used to work at LASP and is now at Goddard, he used Eve data to identify dimmings. But of course, you're kind of blind because you don't know the location and you have very little information. You literally can just say something happened.
But it would be relevant for the spell observation, perhaps.
I'm sure. I haven't used that data. Yes.
Are any of your dimmings, do you have cases where they're not associated with CMEs? Or,
yes.
And if so, what fraction? I mean,
so out of the 154, I would say, so around 60 had no less. A third of the dimmings had CMEs. But most of them don't. And it could be just the fact that, so this is a LASCO CME catalog, which means that a lot of the time, if the dimming is near the disk center, and mind you, I'm trying to look within 60 degrees, so my obscuration is low, that means that a lot of the CMEs are coming towards us.
right.
So if they are small, you're not going to see them. If they're coming straight at us, or you would see a halo. And mind you, I do take a note of halo events, but you will only see them really well, or you will have better mass calculations the more if they're deflected for some reason or they're going sideways. So that is definitely a tricky situation, and that's why quadrature is so important to do this study, to basically repeat this study. But a lot of the time, and I think it might be an observational reason why the dimmings don't have associated CMEs. I mean, okay, let's be honest. There could be two cases. It could be some weird case where maybe the field opened up, there was very little plasma, so you can see a hole in the corona, but we don't see it in the corona images because there was so little material, or because it's coming towards us. The other case is, I don't know, if there's an eruption and the plasma is gone, we should be able to see it. I mean, the plasma have to go somewhere, right?
Maybe like somewhere else on the sun.
But could that well, where? Because if you have an open field, that means that that's gone.
Yeah. Maybe.
Well, that's the thing. There are so many maybes. I don't know. I think that's why it's important to do the right angle study. Yes.
So the timing of the dimming is pretty concurrent with the flare release.
So again, the flare, where I was able to link them. So I looked at the GOES X-ray catalog, and so I linked the start around the start time of the dimming. So I have that information, and I manually looked at the X-ray flare list, and I made a connection. And also they have the location of the flare. So then I knew if it was the same active region, then it would be linked to the dimming if it was close in time. So the time between the start of the dimming and the flare, again, is within a few hours. In this case, in some cases, the flare appeared before the dimming or occasionally afterwards. So it was less, as in CMEs, that the CME always came after the dimming. So it's always a few hours. But I also check the location so that I'm not comparing a dimming from somewhere completely different from a flare that happened to occur at the same time. But of course, there are sympathetic events. So that's a tricky case. When you have several things blowing up and erupting, and then you have a dimming here, a flare there, and that triggers something else. So that's hard.
In the Voyager study that you're about to do, one thing you're really interested in is to see if you can use the Dimmings to infer near the disk center the angular direction of the CME.
Right.
Very useful for space weather prediction to know if the CME is actually in the plane and it's going out.
And I can see that because when I use the Angelos Vorlidis' code, I'm actually creating a cone to wrap the CME. So we will have the information of deflection or direction. Mm-hmm.
Anyone else? All right, that was a lively discussion. Thanks everyone, and let's thank Larisza again.